The ether functional group is best visualized if you consider the water molecule, which has oxygen at its center and two hydrogens coming off of either side of the oxygen. If we were to replace each of those hydrogens with a hydrocarbon group, and it doesn't matter how long the carbon chain is, it could be 1, it could be 1,000. If you replaced each of those hydrogens with a hydrocarbon group, which we'll symbolize with the generic letter R, you would have the ether functional group. In the diagram that you see here, you see R and R1. The subscript number is just used to designate potentially different hydrocarbon groups. Both R and R1 could be the exact same size in terms of number of carbons in the carbon group, or they could be different. The way that we name ethers depends on a couple of things. One, there's the official IUPAC naming convention, and then there's a more commonly used naming convention because ethers have been known about and characterized for quite a while, and there are some that have common names. The IUPAC naming scheme is kind of the catch-all. It can be used whether your oxygen of the ether group is in line with the rest of the carbons, so it's like one big long chain, or if the oxygen of the ether group is positioned more like a substituent to a longer parent chain. Either situation, the IUPAC naming method will work. The common naming convention is best used when the oxygen is at the end of the parent chain, and the entire structure is basically one big long chain. So the IUPAC naming convention names the ether group as a substituent of the longer hydrocarbon chain. So the first thing you need to look at is the two hydrocarbon groups attached to the oxygen and determine which one's the longer one. Whichever one's the longer one is your parent chain. The other carbon group then becomes part of the substituent along with the oxygen. And the way that you name that substituent is by taking the stem name of that shorter hydrocarbon group. So if it's a 1 carbon group, it would be meth, 2 carbons would be eth, 3 carbons would be prop, so on and so forth. And then you put the word oxy on at the end. So a 1 carbon ether substituent would be called methoxy, 2 carbons would be ethoxy, 3 would be propoxy, so on and so forth. And then you name the parent chain. With the common naming scheme, and again, the common naming scheme is best used when your ether group is at the end of the parent chain. You would name the hydrocarbon groups that are on either side of the oxygen and name them as you would hydrocarbon substituents. So methyl, ethyl, propyl, butyl, pentyl, hexyl, with the YL ending. And what you're going to do is simply name the two hydrocarbon substituents that are on either side of the oxygen and end with the word ether. So if you had a methyl group on one side and an ethyl group on the other side of the oxygen, again, alphabetical order prevails here, so you would name it ethyl-methyl ether. For these two examples, try using the IUPAC naming convention, and that's the one that identifies the parent chain and then names the ether group as a substituent to that. So in the first example, we have 2 carbons to the left of the oxygen and 4 carbons to the right of the oxygen. So the 4 carbons would be your parent chain, making it a butane, and your substituent group then is a 2 carbon hydrocarbon attached to your ether oxygen. So that would be an ethoxy group, eth for 2, oxy indicating that it's an ether. And the position number is needed here because right now the ethoxy group is on carbon 1 of the butane. If we shifted it over a carbon, put it on carbon 2, then we'd have a completely different structure. So the position number is needed, and the name of this compound would be 1-ethoxy butane. Pause the presentation at this time and complete the next example on your own, then resume the presentation to check your work. If we take a look at this one, look at the carbon groups that are on either side of the oxygen. You have a 1 carbon group above the oxygen, if you will, and below the oxygen you have an 8 carbon group. And notice that this time the ether group is connected to a secondary carbon. It's connected in the middle of a hydrocarbon chain. And so this is, again, prime candidate for using the IUPAC convention. Your parent chain is going to be your octane. And so the one carbon ether group, the methoxy group, is bound to the parent chain at carbon number 4. So this would be referred to as 4-methoxyoctane. The common naming scheme, again, looks at the hydrocarbons that are on either side of the oxygen, names them as hydrocarbon substituents, and ends with the word ether. So in this case, on both sides of the oxygen, we have a 2-carbon group, which makes them ethyl groups. And instead of saying ethyl, ethyl, ether, you use the prefixes. If you have substituents that are exactly the same, use prefixes to indicate that multiple. So you have 2 ethyl substituents, therefore this one would be called diethyl ether. And if you have different substituents, again, you name them in order, alphabetical order. One other thing to note is that with the naming, typically there haven't been spaces between the name of the parent group and the substituents. With ethers, there are. So you see that diethyl and ether are 2 different words. Pause the presentation at this time, try the next example, naming it with a common naming convention for ethers, and then resume the presentation when you're ready to check your work. If we look at the carbon groups on either side of the oxygen, to the left of the oxygen you have a 3-carbon group, which would be propyl, and on the right you have a 5-carbon group, which would be pentyl. And again, putting them in alphabetical order, your correct name here would be pentyl propyl ether.